Hello viewers, you are most welcome to the eMath learning platform for pure mathematics by Peter Ekaja. I am going to take you through one of the topics in pure mathematics, and that is basically integration. Now this tutorial is going to basically be suitable for the A-level mathematics students. And without wasting time, I am going to basically focus on the techniques of integration. So before we do that, we should first be very much aware that integration is actually the reverse of differentiation. So it means that someone should be well conversant with differentiation before following this tutorial. Now, without wasting a lot of time, now we can begin with the integrals of trigonometrical functions. Now, from the ideas of differentiation that we already have, let us begin by recalling the following. Roman 1, from the derivative with respect to x of cos x, which is given by negative sine x, if we integrate both sides with respect to x, we expect that at the end of the day we can make the integral of sine x the subject. Now, something to recall carefully. Before I write the step of integrating, you need to know that we are going to be integrating this expression here. And this expression represents derivative of cos x with respect to x. So you will be integrating the derivative of cos x with respect to x, but you will not be integrating cos x. Now, when you integrate the derivative of a function with respect to x, you expect to get that very function. So it means I will say integrating both sides with respect to x, I expect to have integral of the derivative of cos x with respect to x equals to integral of negative sine x. Now, from this point, you realize I have kept a negative on the right hand side outside or out of the integral sign, because this negative represents a negative 1, which is silent there. So that negative can be kept out, so that now when we integrate this, like we said earlier on, when you integrate derivative with respect to x of cos x, you expect to come up with cos x as your answer. Now, because it will be cos x, we shall divide by this negative sign so that we make the integral of sine x with respect to x our subject. And so when you do that, you will come up with the integral of sine x with respect to x, giving us negative cos x plus our constant of integration. This c that you see here is our constant of integration, and it is normally what we call an arbitrary constant of integration. So we need to know right away that whenever we integrate sine x with respect to x, we surely get a negative cos x. So that is the first integral that we really need to master. Let's move on and look at Roman 2. From derivative with respect to x of sine x equals to cos x. We know this from differentiation, that when we differentiate sine x with respect to x, we get cos x. It means now we can again integrate both sides with respect to x. When we do so, we shall be integrating the derivative with respect to x of sine x, but with respect to x again, giving us the integral of cos x with respect to x. Now, I'm again going to make the right hand side the subject. I'm going to make integral of cos x the subject, and automatically when we integrate the derivative of sine x with respect to x, we get sine x itself. Because remember, you're integrating the derivative. That is from the definition that integration is the reverse of differentiation. So it means the integral of cos x is expected to be sine x. Then we shall say plus a constant of integration, which is normally an arbitrary constant. So we can make that conclusion that indeed When you integrate cos x with respect to x, you get sine x plus c. Very important for us. Let's move on to Roman 3. We also recall that from the derivative with respect to x of tan x equals to sec squared x, we can now also integrate both sides with respect to x. When we do so, we shall have integral of the derivative of tan x with respect to x, giving us the integral of sec squared x with respect to x. When you do so, automatically, like we said, integrating the derivative of tan x with respect to x gives us tan x itself. So it means we can make a conclusion that indeed, when you integrate sec squared with respect to x, you get tan x plus our constant of integration. Now remember, the constant comes in. Only and only when we don't have the limits of integration. That is why I'm maintaining my constant c as the arbitrary constant of integration for each integral that we have here. Let's move on to the fourth. The fourth one, we can also recall that derivative with respect to x of sec x is equals to tan x sec x. That should be already what you looked at under differentiation. Now, if this is true, I will again integrate both sides with respect to x. So integrating both sides with respect to x, we shall have integral of the derivative of sec x with respect to x, giving us integral of tan x sec x with respect to x. Now again, like we said, when we integrate the derivative of sec x with respect to x, we shall get sec x itself. So it means when you integrate tan x sec x, which can as well be written as sec x tan x as we have it here, you get sec x plus a constant of integration. We move on to Roman 5. Okay, now from the derivative again of cot x with respect to x, which we all know is supposed to be negative cosec squared of x, we can do the integration with respect to x on both sides. And again, we have to be very, very keen with our negative sign here. We have to be very, very keen with our negative sign here, because we are only going to be interested in the integral of cosec squared of x. So it means what we shall now do is, when we are applying the integral sign, we shall keep our negative sign out so that we divide by it at the end of it all. So it now means that we shall have integral of derivative of cot x with respect to x, giving us the integral of negative cosec squared x, but I've just decided to keep the negative out. As you can see here, we have kept the negative out again, and this negative is going to help us for division. When you divide, remember the integral of this expression here, which is the derivative of cot x with respect to x, is cot x itself. So it means at the end of the day, our answer will be cot x, which will be the integral of cosec squared. But remember, we have to be with that negative sign. So we have to indicate that negative sign and note it clearly that when you integrate cosec squared of x with respect to x, you get negative cot x. Note this clearly. I have adjusted with the red ink. There is a negative in that result of ours. Okay, we can now move on to the last one, and the very last one will be from what we know, the integral of cosec x. We all know the integral of cosec x being the same as negative cosec x cot x. So it means when we again integrate both sides, we shall have the integral of derivative of cosec x with respect to x, giving us the integral of negative cosec x cot x. And when you do this again, When you do this again, this negative must be handled with care. So this integral will give us cosec x. So it means at the end of the day, when we integrate cosec x cot x with respect to x, we come up with negative cosec x plus a constant c. So with all these 6 integrals that we have come up with, we need to master them very well for us to have a smooth progress with all other tutorials that we shall be adding on to this. So it is very important that we have a summary of all our 6 results that we have obtained, and this must become part of us. To just summarize it briefly, integral of sine x with respect to x is equals negative cos x plus a constant. Integral of cos x with respect to x is positive sine x plus a constant. Integral of sec squared x with respect to x is equals to tan x plus c. Integral of sec x tan x is as good as sec x plus a constant. Integral of cosec squared x with respect to x is equals to negative cot x plus a constant. And finally, the integral of cosec x cot x with respect to x is the same as negative cosec x plus a constant. Now, these are very important. We need them for us to continue with the next tutorials. Thank you so much. Let us meet again in our next tutorial.